And that brings us to forecasting. So forecasting is when you predict the level of the time series variable in the future. So there's a bunch of different forecasting methods. There's time series models, and we've been talking about trend models. And we will focus on a trend model. We will decompose the trend into seasonality. We will think about seasonality, and we will also look at smoothing models. Okay, we will not use ARIMA models. I'm not sure what that is, but we have a time series and forecasting class that's offered in the fall semester. It's a 4,000 level economics class, and that class gets into this sort of thing. We'll also talk about causal models during this lecture, but we won't be doing much in terms of forecasting with causal models. We'll mostly be forecasting with time series models with trend. So trend forecasting. So there's three kinds of models that we will look at. There's a linear model, where this is a regression model where A and B are estimated regression coefficients. T is the time trend, and Y sub t is the level of the time series variable. The exponential model, which is the exponential is what Excel calls it, it's equal to A times the exponential of B times T. And once you take logs of both sides of the exponential model, we have a model that's where the natural log of the time series variable is the dependent variable in the regression, and the constant represents the log, the natural log of this A value. And then the regression equation is linearized with a coefficient on the time series variable. And the natural log here can be interpreted, the natural log of the time series variable can be interpreted as the percentage change in the dependent variable. So the B coefficient, in the linear model represents the constant change in the time series variable for each change in the increment of time. And in the exponential model, B measures the percentage change in each increment of time. And then there's also a quadratic model, where it's a multiple regression model with t squared as an additional variable. You could also estimate, Excel calls these polynomial models of order 2 for the quadratic, and you can estimate quadratic models or polynomial models of order 3 or more, but the quadratic usually captures much of the variation in a time series. Go back to here, if the quadratic fits the data pretty well. So a linear model, this is the simplest one, and it's usually best for short run forecasting, or as just the first model you estimate, and you call that the baseline model. The linear trends fit by OLS regression, ordinary least squares. Okay, and instead of using the time periods that's contained in your data set, you create a time index. So the first date in your data set, you convert that to a 1, the second date you convert it to a 3, and so on. And that's the independent variable in your regression analysis. And once you've estimated the slope and the intercept, you can just push that line out into the future to make your forecasts. Okay, so here's what an upward linear trend looks like. Your coefficient on B is going to be greater than 0. And a downward linear trend, is what is on the right-hand panel. And your B coefficient is going to be negative. In an external exponential trend model, okay, this is more useful for longer time periods or time series that are growing or declining at the same percentage rate in each time period. Okay, with an exponential trend model, you can compare two growth rates in different time series variables. It's real useful for that, especially if the units of the data are different. Okay, the percentage growth rate is what's known as unit free. So you could be comparing sales in terms of quantities and then changes in another variable in term that's measured in dollars. Okay, so in terms of forecasting, you conduct your ordinary least squares regression, and then you have to transform the intercept back to the original units. So you have to go from the double log model back to the exponential model to get to predict a number that makes sense. Okay, and here's what an exponential trend model looks like. So here, the percentage change in y in each time period is equal to b, and that's positive. So it's increasing, the y variable's increasing at an increasing rate. And then with exponential decline, when b is less than 0, the time series is decreasing at a decreasing rate. All right, so if you're a finance major, you might be already familiar with the exponential model. It's a lot of times it's most useful for financial data. Covers a long period of time. You might have stock market returns over the last decade or two. Like I said, you can compare two growth rates. I'll get rid of that. Okay, and when you don't have a lot of data points, when the time series length is short, then there's usually not much difference between a linear and an exponential model. And then the third model is a quadratic trend model. And you just fit the quadratic with ordinary least squares regression. And you can test for this quadratic term by checking to see if c, the coefficient on the t-squared variable, to see if it's not significantly different from 0. And so, for example, if the t statistic on the c coefficient is less than 1.96 at the alpha equals 0.05 level of significance, or 1.645 at the alpha equals 0.10 level of significance, then you could drop the t-squared term because it's not different from 0. And quadratic trends look like this. So the quadratic model, when b and c are both positive, looks like the exponential model where the trend is increasing at an increasing rate. But if b is greater than 0 and c is negative, then you can estimate these hill-shaped models. If b is less than 0 and c is greater than 0, you can estimate these U-shaped models. And if both b and c are less than 0, then that would fit best a time series that is decreasing at an increasing rate. Okay, and here's just a slide, a table from the textbook that compares the three models and when they're best and when they're and so some good things about them and some bad things about them. And in terms of which model is best statistically, we can appeal to Occam's razor again. So always, if a simple model is about the same as a more complex model, then we prefer the simpler model. Okay, and we'll think about overall fit. How does the trend fit the past data? And we'll use the R squared to determine overall fit. Believability, we want the forecast to quote unquote look right. Okay, you can have a data. Well, I'll go back to that. And then it's real important if you're making a forecast into the future that the fitted data matches the most recent history. Because if not, then the forecast is not going to look right. And I think we're going to be looking at we'll check out some data that to see how that works.